So today I want to go through some of the properties of waves. All right, you've been talking about some of the details about waves, like the wavelength and the frequency and those types of things. But we're going to talk about some of their properties, some of the things that they do, and try to describe those and do some problems with those as well. All right. So right now what I'd like for you to do is let's go over a couple of definitions really quick, just because these are going to be important as we go forward. In just a minute, I want you to pause the video when I say so, and I would like for you to define superposition. Okay? Now I really want you to write down a definition so that when I give mine, you can go back and double check to make sure that you're including all the important pieces. This is good practice because this is a question, this one and the next one are ones that have come up on IB exams before. So here we go. Go ahead, define superposition, pause. All right, so hopefully you've defined it. Here's my definition. When two or more waves of the same type arrive at a given point in space at the same time, the displacement of the medium at that point is the algebraic sum of the individual displacements. Now these are things that we talked about in the last video, right? You need two or more waves. They have to be the same type. They're arriving at the same point at the same time, right? And now what we're talking about, when these two waves arrive at the same time, the medium can't be doing two different things at once. And so what happens is that we get the algebraic sum of the individual displacements. That's what's going to happen to the medium, right? The medium, the particles in the medium itself, the air particles, the water particles, can only be doing one thing at a time. They can't split and be doing two different things. So the wave will combine, the energy will combine in such a way that it's the sum of the individual displacements. And it's okay to have vector here as well. Okay, but we aren't going to be working with anything that you have two-dimensional type things to be worrying about. So it really is just the sum of the individual displacements. But again, recognize it is displacements, not amplitudes, because amplitudes are always positive. We want to be able to make sure to take care of that. All right, next one. Define wavefront. All right, give your own definition right now. Pause. All right, so hopefully you've taken time to define a wavefront on your own. In case you weren't sure, a wavefront is a surface through crests and normal. Normal means perpendicular to the direction of the energy transfer of the wave. So you've got a wave, right? And that wave is traveling in this direction. So a wavefront is just a surface or a mark at that maximum. Okay, you could have a wavefront here, a wavefront here. Okay, it's perpendicular to the direction of the wave. Now the direction of the wave, which is the green line that I just drew here, is actually a ray. All right, now these wavefronts that I've marked, as the wave moves, of course those wavefronts are going to move along in the direction of the wave. But notice that the wavefront itself is perpendicular to the wave. All right, and we're going to see this in the next video as we go forward. All right, so here we go. This is a really, really old video, but it shows what I want to show. All right, so I'm going to go ahead and start it. You're going to hear some music maybe in the background. This is, like I say, this is old, maybe 50s or 60s. Okay, what we've got here is a pool of water. All right, and what this is a wave. Okay, somebody has created a single pulse in the water that's creating this wave. And this white thing here, that big white bar going down the middle of the page, that is your crest. That's your wavefront, right? That is what, because the water is deeper there, it focuses the water, focuses the light so that it looks brighter there. So that's actually the crest. Okay, that's actually, it's the crest and it's the wavefront that we're talking about. Okay, the rays, of course, are moving the direction. Now, this is a reflection, and what we want you to see is that the angle of the reflection is the same on both sides. Usually, we actually talk about the angle with respect to the normal. Okay, so I'm going to show you that here. If you look at the normal here, perpendicular, usually the angle on either side of that is going to be the same. All right. Now, what I want you to see here is the motion, the speed of the ones above and below. Notice that the shorter wavelength is going to be moving slower. The one up above above is moving faster. All right, so I did rewind the video just a minute because I want you to see the one with the two different waves. Notice that the one on the top again will have the longer wavelength, the one on the bottom will have the shorter wavelength. But look at this line right here. Count how many times the wavelengths go through, or the wavefronts go through that line. If you have to rewind the video, go ahead and do it. Okay? What you should recognize is that what ends up happening is the frequency doesn't change. Okay? Now this right here actually demonstrates that. It's demonstrating that the longer wavelengths and the shorter wavelengths all are going to pass through this center point at the same time, going from the water is deeper and shallower. That's why you're getting different wavelengths. Okay? But the important thing is recognizing that they're going to move along at the same rate, right? The frequency is going to be the same, which means that the one with the longer wavelength is going to have to move faster. Okay? So rewind that again if you need to be able to see that. Okay, same thing again here, right? If you look, the one at the bottom has a longer wavelength, the one at the top has shorter wavelength. But again, if you draw a straight line, right? I can't draw a straight line at all. Okay? If you draw a straight line, count the frequency, how often it goes through that line a certain amount of time, and you'll see that they're the same. Okay? Now, we're going to go ahead and look at something slightly different here. Alright? So you can see the spacing right here. Okay? And look at how much it's spread out. Right? It's kind of, you can see how much the wave is spreading out. So now we're decreasing the wavelength, right? So the wavelength is getting shorter. And you'll notice that the clear definition now is it's actually not spreading out as much as it was before, right? And that's an important idea, that when I decrease the wavelength, that it actually isn't going to spread out as much as it did before. Because the wavelength, the size of the wavelength and the size of this opening are important when we figure that out, when we look at how much it spreads out, okay? This spreading out is diffraction. Okay, so we'll talk a little bit more about diffraction later, but that's what we're looking at now is diffraction. See, now the defined area where it's spreading out is significantly less. It is spreading out everywhere no matter what, but the shorter the wavelength, the less it's spreading. So now it's going backwards. We're going to start increasing the wavelength. And again, hopefully you'll see as we increase the wavelength, again, we'll start to see significantly more spreading out there, right? It's very, very clear that the wave is spreading out more at these longer wavelengths, all right? So, that's diffraction for you, okay? Just going to change it again in just a minute. A little something slightly different. Wavelength is going to be the same this time, and we're going to change how wide our slit is. Okay, so right now notice that it's pretty narrow. Okay, pretty narrow. We've got a certain amount of spreading out, right? And yeah, it is spreading out over here as well, but some of that is just due to the water. It's due to the reflection in the water and the various bonding of the water molecules and things like that. What I want you to see now is that as time goes on, right, now look at the spreading out, the well-defined spreading out, right? It is a little bit blurry over here, but like the well-defined spreading out, it's not very clear outside of that, right? That's because the slit is so much wider, okay? Now one of the things that tells us is that diffraction is more significant when the slit is smaller or when the wavelength is bigger. All right? So, hopefully you got that from that video. There's a couple of things that we saw there, and we'll go ahead and talk about it a little bit more in detail in the following videos. All right? So, that's enough for this one. You can go on to the next.